a reminder of what we have so far. So we've been studying what to do with an ordinary triangle. There's one such thing. Just label the angles with the same letter as the opposite sides, but in the opposite cases. And so far we have a few formulas. We have the area formula. Well, one of a few area formulas. What's the area formula for this triangle that we got in class? Flip back in the notes if you need. It's probably something like 1/2 base height, so there's probably a 1/2 in there.
1/2 times BC times the same thing.
Nice. Well, it could be any other triple, as long as you use two sides and then the angle which they give. The other formula we got, which we used pretty extensively, is the law of sines. What does the law of sines say?
A over sine of A is equal to B over sine of B is equal to C over sine of C.
So, if you take the ratio of the side length divided by the sine of the angle opposite, it's the same no matter which pair you pick. And we saw good times to use both of those. To use the law of sines, rather. So if you're given a triangle and you're given if you're given two angles in the side of a triangle, yeah, you can use the law of sines to figure out how to do that. Angles have to add up to 180 degrees, and then you'll be set to use law of sines. How do we do that? Side to side angle. Side to side angle triangles will be other triangles that we use because you'll wind up with angle and side opposite, so you're set up to use law of sines. Whenever you use law of sines to figure out an angle, you need to worry a little bit about the object selection. There are some triangles that this tool is not well equipped for. Let's say I give you a triangle with that certain information. Is that set up to be approached with law of sines? Yeah, law of sines needs you to really know a pair consisting of side and angle opposite. Does this have such a thing? No, so we can't really hit it with the law of sines. Law of cosines will give us a different tool. So, the law of cosines, when I get this, so the law of sines, you should think of as being like the non-right triangle analog of SOHCAHTOA. You could really interpret this as saying like the ratio of two sines is the ratio of two side lengths. So that's like what SOHCAHTOA tries to capture. The other important thing we have about our triangles is the Pythagorean identity. A squared plus b squared equals c squared. Law of cosines tries to capture that. So, here's what the law of cosine says. I don't know, like a lot of people have seen a lot of the things that we do. How many people just already have the law of cosine as something that they remember? Cool, let's hear it.
I'll see it or I'll recognize it when I see it.
Yeah.
I'll remember it off the top of my head.
Fair enough. Let's write it down. So here's what the law of cosine says. And I'll start by just like writing down what the Pythagorean identity would say. So imagine this angle theta, which is not a right angle, one right angle. Then I would see c squared equals a squared plus b squared. But that obviously can't be right, because right, that's only true for right triangles. So there's going to be some like error on that shows up. That error on is that c squared is a squared plus b squared minus 2ab cosine of whatever that angle is. And I said this should make you think of like the Pythagorean identity, and let's see what happens if we like do the extreme choices for this angle theta. If theta is 90 degrees, or however you want to say a right angle, pi over 2 radians, what's the cosine of a right angle?
0.
0. So what does this formula become if theta is a right angle?
A squared plus b squared plus c squared.
So we'll look at the Pythagorean identity. And what are the other two like extreme choices? So you can't like literally see zeros aside in a triangle. Let's think about like what you would think would happen if theta's like really close to 0. So if you know that side length and this side length, and this is really close to being just 0. Let's make the side length seem something different. And what should that result in C be? Should get really close to like, there's the side length A, maybe the side length B is shorter, and then the side length C, I guess, has to be this distance. So I think C should be like A minus B or something. Let's see if this does the job. So I should see A squared minus B squared minus 2AB. What's the cosine of 0? So times 1. Oh, so C squared is A squared plus B squared minus 2AB. But what's A squared? What the right hand side? What does that make you think of now? Does it factor? How does it factor? Well, maybe I'll write down factoring and then like we'll verify. Does that seem correct? Right, like formula this side. A squared first. Outside, A times minus B, that's minus AB. B times A minus AB. Negative B times negative B is going to give you B squared. Yeah, so that's right. Oh cool, so that means C squared is A minus B squared. If you just wanted to get A out, what would you do?
Take the square root.
Take the square root of both sides. It's either plus or minus A minus B. Oh, does that agree with what we found down here? Now we got like A minus B on the nose. Otherwise it would be B minus A, which is the negative choice. Oh cool, so it even predicts like the correct thing for the extreme values. Alright, nice. So, as per usual, I'm not going to attempt to explain why the law of cosines is true. Instead, I'm going to advertise that there's a bunch more extra credit. You want to see why the law of cosines is true? Start with the triangle. Split it into some right triangles. Now do, I guess, the Pythagorean formula to that, but like a few times. And eventually you'll just get it straight. Instead, let's use this to do some computations. There's a triangle problem. I guess I've labeled the unknown side C. Law of cosines looks well to solve that. Nice. And maybe I'll give y'all a choice. I can be quiet for a bit. You can apply law of cosines if you feel comfortable. Or I can talk to them. People want me to talk? Cool. Then I will. So, the law of cosine says this. C squared equals A squared plus B squared minus 2AB cosine theta. Well, there's a side. It's called C. It doesn't matter what it's called. C squared equals A squared, 3 squared, plus 5 squared, minus 2 times 3 times 5 times the cosine of pi over 30. Alright, so that's like just writing down and matching the symbols. And like, I guess I could do the computation, but I'd rather be quiet and not you telling me to calculus on the computation. So once you work out what C should be, we'll come together. You have an exact value or a decimal approximation to tell me, let me know.
Does your calculator need to be in radian mode because of the pi over 3?
Ooh, that pi over 3, is there a degree symbol next to it? That means it is definitely in radians.
Beyond 7.
On the nose?
Yep.
Oh, that's kind of cool. I guess I didn't need the approximate sign. Do I hear a second or 7? Do I hear disagreement with 7? What'd you get?
Root 19.
I hear a root 19. Do I hear any other options? Do I hear agreement with either of those options? Which one? The second one? Alright. So, let's go through and see what happened. Let's just compute left and right. 3 squared is
9.
5 squared
25.
minus 2 times 3 times 5. Let's see, that's like. Let's actually just walk out what cosine of pi over 3 is. What is cosine of pi over 3?
1.5.
1/2. Either by calculator or by units auto. How many people took out the units auto? How many people use the calculator? How many people have just like engraved the units auto in their brain at this point? Yeah, that's like my goal. You look at it enough times and eventually you just know it. Alright, so 2 times 3 times 5 times 1/2. Wait, let's keep walking left, right. The 2 and the 1/2 can cancel. Do you see something going wrong?
Yeah, I added and subtracted.
That'll happen. Gosh, so I guess like all of that should add / subtract to be 19. Oh, cool. So it is in fact root 19. I don't care about the decimal approximation. Groovy. So, maybe we'll even say this. At this point, we know C is equal to root 19. Let's label these missing sides. I guess that should be like A and B. Is there enough information in that diagram to figure out side length A and side length B? Let's not actually like literally do it, but what strategy would you want to follow?
Use law of sines.
Use the law of sines. And remember, when you use the law of sines, you always have to worry about the possibility that an angle might be obtuse. And it's better if you can just like explain away that worry and just say one of these angles can't be obtuse. So which one should you use law of sines on first?
A.
Side theory is shorter than side 5. Well, I guess this triangle is not drawn to any sort of like reasonable scale. Theory is probably not longer than 5. You use the law of sines to get the angle A, and now after you know A, how would you find the angle B?
Minus A.
Nice. Except it should all be in radians probably, well, all in degrees. So instead of 180 it would be pi minus. Groovy. get the angles sum to pi coordinates. Groovy. So you can solve triangle problems now. And maybe I'm going to point out one common mistake I see when using law of cosines. Those two need to be opposite each other. So law of cosines is really good if you want to find this unknown side C opposite a known angle. Or do you think you could use this to like find the unknown angle if you knew all three sides? Yeah, because you can take inverse cosine of whatever cosine is. In fact, here's like a little flowchart. Suppose someone asked you to solve a triangle problem. They told you three things about the triangle. If they just told you all three angles, well, like, you don't have enough information. So it could be that triangle, or it could be that triangle scaled up. You need more information. If you know two angles and a side, then that's what we did like a while ago. If you have a side angle triangle, this is like the complicated case. You use the law of sines to determine the unknown angle. You worry, well, maybe that angle might be obtuse, so maybe there are two solutions, maybe there are none. Once you know the second angle, you can find the third angle because they will add up 20 degrees, or pi radians. And then law of sines to find that last side. Do you think you could also use the law of cosines to find the last side if you know everything but one side?
Yeah.
Yeah, very good. Yeah. Whichever one you like better, I think law of sines is probably a little bit less because law of cosines you have to like square stuff, you can square root. If you have a side angle side triangle like this one, you can use the law of cosines, no inverse trig involved, to find the missing side. After you know all of those, you can use either the law of sines to find the missing angles, or the law of cosines to find the missing angles. If you know all sides in a triangle, then you can use the law of cosines to find all the angles. That feels pretty good. And in fact, let's just do some examples. Here's another triangle problem. You'll notice that all of my triangles are the same underlying picture. I just relabeled the sides. It's because not doing that would be like really annoying and super unlimited benefit. So I guess the takeaway here is don't rely on this picture to tell you how big those angles should be. Let's try to use this. There's a triangle. I know all three sides. So I'm not in a situation where I can use the law of sines. I don't know that opposite pair, don't know that opposite pair, don't know that opposite pair. But I am set up to use the law of cosines. And let's, I should have done law of cosines on the body. So what's law of cosines say? It says c squared should be a squared plus b squared minus 2ab times the cosine of. And flip back to the previous page if you need to remind yourself, what's the angle that I should put in these parentheses?
The angle opposite of C.
The angle opposite C. And in that picture, which one is that? In the picture on the board. Nice. But your like verbal description was more useful, so let's point that out. So now that we have that on the board, let's start using the law of cosines to find the missing angles in this triangle. And I think the way I want to do this is like, we'll do one all together. Then the two remaining ones will be like super similar amounts of work. So I'll break y'all up into groups and y'all do it. And then we'll come back together and check by seeing if our angles add up to pi radians or 180 degrees. So, first things first, it looks like it's probably the exact same work to find any one of those angles. So I think let's just go top to bottom. Let's talk through the angle alpha first. So, I would like to know the angle alpha. That's my first goal. Which side is opposite that angle? 4. So let's use the law of cosines based on this side. So 4 squared equals 6 squared plus 3 squared minus 2 times 6 times 3 times cosine of alpha, which I don't know. Ooh, and I'm going to do something incorrectly, but it's an incorrect thing that I see an awful lot on stuff like exams when I ask people to use a lot of cosines this way. Here's the very incorrect thing I'm going to do. Well, this should be the same as, so this is me making mistakes, so don't necessarily take notes here. 46 plus 9 minus, gosh, 2 times 3 is 6 times another 6 is 36 cosine alpha. Let's see, 36 minus 36 is 0, that's 9 cosine alpha. And that's apparently equal to 16. So it looks like 16 over 9 should be cosine alpha. Oh wait, that's kind of like really bad, isn't it? It says that cosine is bigger than 1. So that suggests there are no solutions, which would mean this would be like a really badly designed problem. It would be like the first thing I do. So probably there's something that's just wrong in that block. What's going on?
36 is multiplied by cosine alpha.
Yeah, and the other is a garbage.
Yeah, the 136.
Yeah, this 36 is multiplied. So remember, order of operations is incredibly important. You have to resolve the multiplication before you resolve addition. So, all of that's really bad, and if you do that on like the corresponding problem on an exam where I ask you to use the law of cosines, you'll probably just get no points. So don't do that. So let's go correct it out. Here's the thing we want to solve. So I guess like cosine of alpha, that's like, we'll treat that as the unknown. I want to get that on its own. So, what should I do if I want to get cosine of alpha on its own here? Well, I guess getting to like this step was fine, right? There was no mistake yet. It was the next step that's one wrong. So, all of this is equal to 4 squared. You want to solve that for cosine of alpha. What do you do? Equals 12 plus 9 is 45, right? Alright. 45 minus 36 cosine alpha. So you can combine those together. Alright. You want to solve that for cosine alpha? What do you do?
Subtract 45 to the other side.
That seems good. Subtract 45 to the other side. 16 minus 45 equals 46 cosine alpha. Gosh, and 16 minus 49 is negative 29. And in reality, you should be careful on that because it'll affect the finalizer by hot seconds. Alright, so what next?
5 by negative 36.
Divide by negative 36. Ooh, because I lost a negative sign in that. So divide by that, double negatives will cancel. I'll get 29 over 36 equals cosine alpha. Alright. So cosine of alpha is on its own, so I now see cosine of alpha equals 29 over 46.
Take the inverse.
Let's take the inverse cosine, and then we'll also reflect on whether there are more solutions than that. So I'm getting alpha to be cosine inverse of 29 over 46. Maybe we should also decide, do we want this to be in radians or degrees? Radians? Degrees. Well, there was a tie vote 2-2, so I want someone additional to vote. Radians. Degrees. Okay, degrees half. So what is that in degrees?
$36.34.
About 46.34. 34 degrees. Cool. All right. And let's take a moment and reflect whether that should be the only possibility. And let's do it by thinking about what the range of cosine is and what angles you can see in a triangle. So this is off to the top again. What's the range of cosine?
Cosine inverse.
Yep, what's the range of cosine inverse? That's of course what I meant.
0 to pi.
0 to pi. What angles can you see in a triangle? 0 to pi. Maybe you can't literally see 0. And pi is like 180 degrees. You can't quite get 280 degrees because then you like totally pull the triangle out. Oh cool, every possibility here is in the range of inverse cosine. So there's not like this weird, it doesn't catch the obtuse option. This is the only option. Ruby, nothing you can do one of the remaining on your own? Or maybe with some amount of collaboration from those around you? Cool. I'm going to split us roughly down the middle. If you are in the literal middle, then I guess you get to pick. Determine for me the angle beta. Determine for me the angle gamma. Where, that part I know, that part I can. I guess those of you who are in like the middle can even like do the check in item D. So, let's see, amongst the people who are resolving beta, how many people feel like they're about done and have an answer? Cool. Of the people who computed gamma, how many people feel like they have an answer to gamma? Cool. If anyone is seated next to someone who's computed the other angle, also take a moment and see if the totals add up to 180 degrees or pi if you're on a radian mode. Cool. I see some happy nodding of head. That's good. Let's go through and write it down now. So, beta equals and is approximately. What do we get for beta?
117.27 degrees.
About 117.27 degrees. And what was it on the nose? What did you plug into the calculator to get that?
Inverse cosine of negative 11 over 24.
Cool. Do I hear a second for either or both? Nice. So here's the thing we're pointing out. That's like a negative number and a cosine, inverse cosine. And let's just see what that should mean. So let's see. The graph of inverse cosine, what, like, looks something like that. So a negative input resulted in an output that was bigger than pi over 2, an obtuse angle. Oh, cool. So when this is negative, that will be obtuse. And let's go ahead and like just check if that could be obtuse. The angle beta, is it opposite the longest side length? Oh, cool. So it's allowed to be obtuse if it wants to be. So it's not obviously long, but that's obtuse. Any calls to do any of the work on computing beta? Cool, let's do it. So talk me through it. What equation did you start with to compute cosine of beta? I'm going to switch colors.
Log cosine.
Log cosines. Cool. Tell me what equation it is you worked on using log cosines.
6 squared equals 3 squared plus 4 squared minus 2 times 3 times 4 times cosine of beta.
Nice. Alright, so there's the angle you wanted to know. There's the side that's opposite. This needs to be the thing that's opposite the angle. Cool. And now that that's written down, it's a matter of like doing the algebra. So I don't know. Do you want to talk through like doing the actual algebra to get cosine on its own? Yeah, I guess like this doesn't cost you 46 from the 6 squared. Let's subtract 9 from 3 squared. We'll subtract 16 to the other side. So it's negative. Gosh, 2 times 3 is 12 times 4 is 48. Oh, and now you've got to divide. 46 minus 9 minus 16 all over negative 48 is cosine alpha.
Should be 24 instead of 48 because 2 times 2 times 4. 24.
Agreed. Thank you. That's what I get for trying to do things too quickly. Alright, nice. And then I guess all that simplifies to negative 11 over 24. Alright, gamma. What did you get for gamma, both as the exact value and an approximate value?
Inverse cosine of 43 over 48,
Inverse cosine, 43 divided by 48.
which equals about 26.38.
26.38. Cool. Do I hear a second for that as the total? Nice. Do I hear a call to go through the work to find gamma? Oh, cool. Let's just do one last checksum. We have these approximate values. Let's see what they add up to. So let's see, that's 36.34 plus 117.27 plus 26.38. And on the one hand, like, adding together 4 or 5 digit numbers isn't that hard. But we also have a machine. So what do you get when you add those up?
179.99.
Do you want to hear a second for that same total? Oh, cool. That's not like exactly equal to 180 degrees. Is that bad? Yeah, well, these ones exactly equal to the angles, right? When you use approximations, maybe you'll be off. Good. Feel good? Nice. So, what's the point here? If you want to use log cosines to find all of the angles given the side, given the values for the lengths of the sides, you can use the log cosines to find any given angle. And maybe we'll even point this way. After we got the angle alpha, could we have used log sines to find the other missing angles? Yeah. I guess something might have gone wrong when determining beta, because it turns out beta had to be obtuse. So log sines would give us that weird situation where there's like 1 or 2 options. And we know there's not really, there's only one option. That is what beta has to be. So, when using log sines in this situation, like, be careful, like log sines sometimes predicts 2 options. It won't tell you which one's right. We don't. Alright, so, there are 2 last things I want to do with today. Let's do some, like, applied feeling problems. Because, right, like, all of this stuff is what things like triangulation, a bunch of navigational things walk on. And let's just see some examples of that. While walking in the woods with Robert Frost, you come to a fork in the road. Robert Frost takes the path less traveled by, which makes all the difference. You take the path more traveled by because, like, it looks better. Due to path maintenance issues, you go faster than Robert Frost. He maintains a pace of 30 miles per hour, while you maintain a pace of 4 miles per hour. The path's divergent 45 degrees. I would like to know, after 1 hour, what's the distance between the 2 of you? So, I don't know, like, this is very much a word problem, and it's very geometric. So maybe a picture is a good place to begin. So, what sort of picture should we draw? Yeah, it's probably a triangle it's gonna draw. And maybe I'll even draw a piece that's totally experienced in the problem. You walk together, you come to the fork in the road. And as Yogi Berra once said, when you come across a fork in the road, take it. The paths diverge at 45 degrees. I guess it doesn't matter which one's which. After 1 hour, you want to know the distance between the 2. So there's like a diagram that has some of the information. What else could we add to that diagram?
The lengths of the 2 lines that are drawn.
Nice. Lengths of those 2 lines. How far are they?
4 miles and 3 miles.
Because you're traveling 4 miles per hour for 1 hour. So like going from speed to distance is even going to be easy this time. Because you walk at a rate of 4 miles per hour and you travel for 1 hour. Yeah, you cover 4 miles. Alright, so let's add those to the diagram. Should I include the units in the diagram? People have a preference?
Have a great Thanksgiving.
I think I won't for space reasons, but like.
Where are you going?
So Robert Frost covers 30 miles, you cover 4 miles. You want to know the distance. oh cool, that's a triangle where I know 3 facts about it. And it's not all 3 angles. So I know I can compute the distance, it's a matter of figuring out how. Do I use the law of sines or law of cosines in this situation?
Cosine.
Law of cosines, right? You can't use the law of sines. Law of sines needs you to know like opposite information, and we don't. So we need to use law of cosines to determine the distance. Law of cosines is on the board. So I want to determine, let's use the law of cosines. So I want to know the distance. So I guess distance will be my variable name. Law of cosine says that side length squared equals sum of the squares of the other 2 side lengths minus 2 times side length times cosine of angle. So I guess that means we just got to write that all down and see what happens. And happily, I see that people are just like going for it. So I think I'm just going to be quiet for a few moments. Let's see. As you start feeling stuck, feel free to ask questions of each other or raise your hand, I'll come to you. Once you feel like you have it, then we'll come together. Alright, cool. Let's see it. Exact value or decimal approximation of the eventual distance. What do we get? Is there a call for me to do the walk? Cool. Let's talk through it. Let's start by just going down the law of cosines. So distance squared, that's like the C, is the sum of the squares of the other 2 sides. So that's 3 squared and 4 squared. Minus 2 times side length times cosine of angle. 2 times 3 times 4 times cosine of 45 degrees. Alright. Feeling good so far? And like, the algebra here is like automatic. I'm just going to take the square root of both sides eventually, because I need to get rid of the square on the distance. So most of the walk's just going to be simplifying this side. So, I guess you just got to do it. 3 squared is
9.
4 squared
16.
minus 2 times 3 times 4 is exactly the thing that I screwed up and said 48 on there. Cosine of 45 degrees is
2 root Root 2 over 2.
Root 2 divided by 2. So I think you said it was bigger than 1, so it's not a possible value for cosine. Cool. I guess we can simplify this side a little bit more. What's 9 squared? What's 9 plus 16?
25.
Alright, so distance squared is 25 minus, oh, I can simplify that. What's 24 divided by 2?
12.
12. Root 2. Alright. So if d squared is equal to that, how do you get d on its own?
Square root of this guy.
Take the square root of both sides. And theoretically, you know that like the square root can accidentally kick out a plus or minus sign. But would it make sense to use the negative choice here? No, negative distance doesn't mean anything. Oh, cool, so there's an exact value. And that's just a matter of plugging it into a machine to get a decimal approximation. What is that?
About 2.834 miles.
Cool. And I didn't specify how much precision, that seems like funny. Especially since, like, what do you think the chances are that these spaces were exactly 34 miles, or that that angle is 45 degrees on the nose? That's honestly probably more precision than you should expect. Cool. All right, one last one. This one is less flavor. But all right. You travel due east 3 miles. You then make a turn at 45 degrees to the north. You travel 1 mile forward. Okay, you think I started point. And I guess like we could do like the same sort of thing. There's the side that you'd like to know. You know 2 of the sides. Do you know the angle opposite that unknown side length? Yeah, cool. At least as long as you can do subtraction, I guess. In fact, what is that opposite angle?
150.
150, because these two should add up to be 180 degrees. 150 degrees is what's left. Oh, cool. Is that like everything you need to use log cosines? Yeah, let's do it. So, log cosine says unknown side length squared equals the sum of the squares of the remaining 2. Minus 2 times side length times side length. Times cosine of 150 degrees. And maybe I'll even do this sanity check. That angle 150 degrees is like pretty obtuse. So that means that the side length D should be the longest side length in this triangle. And it's even like really close, it's reasonably close to 180 degrees. I think it'll be pretty close to just being the sum of the other 2 sides. Right? It can't be bigger than 4 miles because of the triangle inequality. If you add up 2 side lengths of a triangle, that needs to be at least as long as the missing side length. Oops. So, oh gosh, I see people just like going for it. Should I talk to it? Maybe in the interest of time, it's just 10 there. So I'm getting d squared is 9 plus 1 is 10. That adds up to 10. Minus 2 times 3 is 6 times. What's the cosine of 150 degrees? Negative root 3 over 2. All right, cool. Seem pretty good so far? All right, so d squared is 10 plus, double negative becomes a positive, 6 divided by 2 is 3. 3 root 3. So apparently d is just the square root of 10 plus Dewey with Dewey. And there are some algebraic tricks to like split that up into two different square roots, but for now I'm happy with that. Alright, so 10 plus Dewey with Dewey.
3.9.
Next, what are the units?
Max.
Right here a second? Nice. Yeah, so that's like about what we expected. It's really close to just being 3 plus 1. We didn't make much of a pond, but we were going really close to just a straight line. But it only waterfall because of the triangle inequality. Nice. Cool. So let's see. I've got my office hour today. I've got an office hour tomorrow. And then there's like no classes for the next 3 days. So, anyone planning on coming by my office hour for the next 2 days? Okay, then enjoy your way. I hope it is restful. Someone else is going to put it on class.
Yeah, for that. That was funny. Keep running into that chair. Yeah.
I have nothing to class last night. Yeah, I'll look into that today.
If like, you still can't tomorrow, then give me a phone.
I do something as awful like that, a lot like that with my afternoon class. I walk to this class, look in, see, those are my students. I have to walk to the other side. Oh yeah, I guess this is fucking like
And then usually I talk with like over there.
yeah, I'll have my class over this week, so. Have you been all the way back home?
Not like all the way back there, because I don't have any classes back there. But like, I have 2 classes in that area.
What I want to propose to do with today is I have what I think should be a reasonably interesting